Okay, welcome to the video lecture on chapter 3. In this chapter, we are going to introduce an important tool, which is the tool of typical sequences, which will be very useful in proving the theorems like the channel coding theorem and the source coding theorem for a certain class of channels and sources, in particular for memoryless channels and memoryless sources. I have to say for the records that these results can be proven also using different approaches. And some versions of these proofs are in fact more powerful because they give more precise results on the behavior of certain quantities, like for example error probability and distortion, and they also can be extended to wider classes of channels and sources. Here we restrict to this style of proof that is based on these typical sequences tools essentially for simplicity, because this is a relatively easy way of proving these results, although it's not the most powerful and the most general. So, what are typical sequences? So, consider to have an alphabet, let's say a finite alphabet x, and we consider sequences of length n over alphabet x. We call them x boldface, means vectors. Those are not random vectors. This is a fixed sequence. So for example, if x is, I don't know, a, b, c, well, and I consider n equal to 10, well, the sequence x could be a specific sequence a, b, a, c, c, a, b, 1, 2, 3, 4, 5, 6, 7, 8, and then, okay, so this could be an example, and of course you may have many of them. How many? Well, in general you have cardinality of x to the n possible. Okay. Now, suppose that we count the recurrence of the symbols in x. So we take all the positions I for which the ith symbol is equal to a specific symbol x. We take the cardinality of this set. This is the amount of times the symbol x appears in my sequence. For example, I can count the recurrence of a symbol A in this sequence, and these will be, I mark them in yellow, it's 1, 2, 3, 4 times. Okay? So when this x indicates the letter A, this cardinality is going to be equal to 4 in my example. And of course you can generalize this to any letter and to any length. So for a given sequence of length n, we can count how many times a given letter x appears. This is called the empirical count. And then when we divide by the length of the frequency, of the sequence, so when we divide by n, this ratio is called the empirical frequency of the letter x in the sequence bold x. And we denote this quantity as pi of x given the sequence we are looking at. And of course, you can do this for every letter of the alphabet. So for a given sequence, we can list those empirical frequencies. So in my example, for example, here for this specific sequence, I have for the letter A and B and C, we said already that the empirical frequency of A is 4 divided by 10, so is 2/5. For so this is the alphabet X, this is the empirical frequency pi. For the letter B, I have 1, 2, and 3, so I have 3 over 10. And for the letter C, 1, 2, 3, I have 3 over 10. Okay, so this is clearly something that is defined for every fixed sequence on a given alphabet. And the collection of these empirical frequencies is called the type of X. So, of course, for a given type, so if I fix those frequencies to 2/5, 3/10, 3/10, well, there are a lot of sequences that have the same type. In fact, every permutation of this sequence has exactly the same type. Okay? Good. So now we are interested in what happens when we take now a sequence generated at random. So we take xn to be a random IID vector where the components are distributed according to a certain distribution px. What happens to these empirical frequencies when n becomes large? Well, it turns out that by the law of large numbers, each empirical frequency converges in probability to the actual corresponding probability value. So now, at this point, you may say, what is the law of large numbers? Good question, because not all of you may have attended my course of last semester. So I'm going to add a page and just say quickly, without proofs, anything, what is this law of large numbers and what it means convergence in probability. Okay, so in general, if I have if I have a sequence x1, x2, xn of IID random variables, and I consider let's say just a function. So this function is a nice, well-behaved function from x to whatever, to the reals, for example, so to r. Okay, x is a discrete finite alphabet, and then I consider the following empirical mean. So 1 over n sum over I of g of xi. Now, those are random variables, so g of xi is also a random variable. This is a sum of random variables, so the whole quantity here, this empirical mean, is a random variable, okay? And the law of large numbers says that when n goes to infinity, so this quantity tends to the expectation of gx, where x is distributed according to px, which is the common distribution. So all these random variables have the same PMF, px, because they are IID. Okay? So of course, this is a random variable. This is a deterministic quantity. So the question is, in which sense we have this stochastic convergence? You remember we already discussed this thing last week with talking about the convergence of the rate of Lempel-Ziv. In this case, the convergence was with probability 1. Well, here this would also converge with probability 1, but we don't need it in this context. We don't need it. We need a weaker form of convergence, which is called convergence in probability, which means the following: that you can prove that limit for n going to infinity of the probability that this random variable, let's call it, well, let's write it explicitly, 1 over n sum of gxi minus this deterministic limit expectation of gx in absolute value is greater than epsilon is 0 for every epsilon greater than 0. So in other words, this means that if I fix epsilon, I take any epsilon I want, fixed, I don't know, 0.00000000001, very small, and then I consider the limit of this probability. This is the probability that this random variable, this empirical mean that we have defined, is away from this deterministic value by more than epsilon, either on the plus side or on the minus side, because in absolute value. So if the deviation is more than epsilon, well, this will be an event and we has a probability. Well, when n goes to infinity, this probability tends to 0, so the limit is 0. Okay? This means convergence in probability. And it turns out that here the empirical frequencies can be written in the following way. Right? The empirical frequency applied to a random sequence. So what is this? Pi x is a fixed symbol and the sequence is random. Well, these can be written as 1 over n sum over I, and then here we put simply an indicator function which is equal to 1 every time xi is equal to the letter x. And of course 0 if it is not equal. So this is a counter that counts how many times xi is equal to a fixed letter x. Now you see that this is just a specific function g. So this is exactly in the form of an empirical mean, and this will tend to its ensemble mean, but the ensemble mean of an indicator function is simply the probability. This is a general result that the expectation of an indicator function is the probability of the event. If I have an indicator function 1 of event A, where A is an event in a probability space, and this is a binary random variable which is equal to 1 if A happens, 0 if A does not happen, okay? Then the expectation of the indicator function of A is simply the probability of A. Now here the event A is, in our case, the event that xi is equal to small x, and since those are identically distributed, these probabilities are all the same, they're independent of either, simply the probability mass function calculated at the symbol x. Okay? So by the weak law of large numbers, we know that if we take a random sequence and we create these random variables, which are these empirical frequencies are random variables, and are in the form of an empirical means, well, these empirical means, they all converge to their ensemble mean, which is exactly equal to the probabilities. We use this symbol here, this symbol P on the equal, that means this limit holds in probability. And here you have what it means, what I have said here. Okay, so that's a fact. Take it as a fact. Here I'm not proving the weak law of large numbers, but that's a fact. Okay, so we may assume that or we may expect that if I take a long random sequence, the empirical frequencies for all the symbols are close to the true probabilities, I can define a typical set, which is the set of sequences, deterministic sequences, whose empirical frequencies is close to the true probability. So this is like the sequences that behaves typically in the sense of empirical frequencies with respect to a certain probability distribution, a certain PMF PX. So we define the epsilon typical set. We fix an epsilon greater than 0, and then the set denoted as T sub epsilon with an n, and here the x indicates that we are considering as a reference probability mass function Px, which is a given probability mass function. Well, this is the set of all the sequences of length n over the alphabet x with empirical frequencies in absolute value close to the corresponding probability value less than epsilon times the probability value. Okay, that's the definition. So in other words, given a set of all possible sequences of length n over this set, and given a probability mass function over the set, we can identify a subset of all possible sequences that have a typical behavior in this sense. Their empirical frequency is close to the true probability for every letter of the alphabet. Okay? Now, we have immediately some interesting properties here. One is called the typical average lemma that says, given x in the typical set, so all sequences in the typical set are called typical sequences. I should say epsilon typical sequences, but you know, when epsilon is clear from the context, I will not say it all the time. I will just say a typical x. This means x is a sequence in the typical set. So given a typical x and given a function g, it turns out that the empirical mean of the function g over the sequence x is trapped between 1 minus epsilon and 1 plus epsilon times the true mean, the ensemble mean. How do we prove this? Just, well, I say homework, but let's give this as an example. Okay, why is not sliding anymore? Okay, this thing sometimes doesn't work. So I'm gonna add another page here. Okay, let's prove this typical average lemma. So what we know, well, if x is typical, then for every letter in the alphabet, we have that the empirical frequency is close to the corresponding probability. And this, if I expand this absolute value, means that the empirical frequency, you can simply expand the absolute value with a plus and minus. Every time you have an absolute value less than something, it means that the quantity inside the absolute value is between minus that something and plus that something. So you do this, and then you write it simply bring terms around. Say you have that the upper bound is 1 plus epsilon times the probability, and the lower bound is 1 minus epsilon times the probability. Okay? So this is true for every symbol x in the alphabet x. for our typical sequence, X sequence, so this one. Okay, and now I will simply write down the expectation. So the empirical mean, I write it as 1 over n sum over I of g xi. These xi's are the letters of the sequence X. Okay, so the sequence X contains letters x1, x2, xn, and here we are simply just summing over these values. Now I can rearrange these values and write them as simply sum over the alphabet, and then simply I count, all the terms for which xi is equal to x will give me the same value of g. So I can collect them. I just multiply by their multiplicity and then divide by m. So I have that this is simply given like this. Okay, simply by rearranging terms and collecting all the terms with the same value of g, I obtain this. At this point, if I use this upper bound here, I have 1 plus epsilon sum over x px gx, but this by definition, this is the expectation. So I have 1 plus epsilon expectation of gx. Okay? And this proves the upper bound. If I use in here the lower bound, I get the lower bound. So this proves very simply the typical average lemma, which means that basically if I have a typical sequence, where is that? Oh, it was here. Okay. If I have a typical sequence, the empirical mean of a given function on that sequence cannot be too far from the ensemble mean. So it has again an expected behavior in that sense. The deviation of the empirical mean from the ensemble mean is between 1 minus epsilon and 1 plus epsilon. Okay. Then we have another result, which is in fact, if you want, a consequence of this one, which is called the asymptotic equipartition property, or AEP, which says that for a typical sequence X, its probability is essentially 2 to the minus times the entropy. So it's between 2 to the minus times the entropy plus delta and 2 to the minus times the entropy minus delta, where delta is, we don't really care about what function of epsilon is. The important thing is that this delta goes to 0 when epsilon goes to 0. Okay? So we write that with this symbol, with a dot equal, means exponentially equivalent, because the main term in the exponent is, in the exponent means that, okay, you have n becomes large, so this exponential goes to 0 at an exponential speed, which is the coefficient of n inside the exponent, and the main term in the coefficient of x is the entropy, because the plus and minus delta can be made as small as you want by simply choosing epsilon smaller and smaller. Okay. How do we prove this? Well, we can do in many ways, but a very direct way is to use just this typical average lemma, because we simply choose as a function g, we choose minus logarithm of p sub x of x. So what do we have? Well, we have that 1 over n sum over I of minus log p sub x of xi is in between 1 plus epsilon. What is the expectation of this function? Is the entropy, by definition of entropy. If you go back to the definition of the entropy, you see that if expectation of g of x random variable is exactly the entropy. And so we have this, okay? Now all what I have to do is to multiply by minus, so I have 1 plus epsilon here with a minus, then greater or equal. Then I write this 1 over n. Actually, I multiply also by n, so let's put here an n minus n here. The sum of log of p can be written as, you know, the log of the product, and here I have minus n 1 minus epsilon h. And now, what is this? Well, because the sequence are IID, this is simply p xn of x. So the product of the marginals in this case, because the sequence are IID, is the joint probability of the sequence x. Then I take, well, that's a logarithm, of course, right? And then I take exponential on all the sides. So what I have is that the lower bound here is 2 to the minus n. I write this as follows: h plus epsilon h less or equal than p n x 2 to the minus n h minus epsilon h. Now all what I have to do is simply call this delta epsilon and this delta epsilon. Of course, this goes to 0 when epsilon goes to 0, and then I'm done. Okay? So this is called asymptotic equipartition property because it says that the probability for all typical sequences is essentially the same, is 2 to the minus the entropy with some little fluctuations, okay? Which means that the probability mass, when n becomes large, tend to be distributed equally among all the typical sequences. That's why it's called equipartition. Imagine that we have a total mass of 1, which is the probability mass, and this is distributed over all possible sequences. And if I take the subset of typical sequences, well, they are almost all equiprobable. Okay? Then we can prove results on the cardinality of the typical set. How large is the typical set? Well, it turns out that the typical set is essentially large as 2 to the n times the entropy, because we can prove that for every n and every epsilon, we have this upper bound, and for every epsilon and sufficiently large n, we also have this lower bound, which means that if I fix epsilon and I take n sufficiently large, when you compare these two guys, right, upper bound and lower bound, basically the typical set for large n and fixed epsilon is exponentially given by 2 to the n times the entropy. Okay, because this 1 minus epsilon can be made as arbitrarily close to 1, and these deltas, plus and minus deltas, goes to 0 when epsilon goes to 0. Okay? Good. How do we prove this cardinality results? Let's do it because it's instructive. So let's prove first the upper bound. So we can say 1 is equal to the sum over all sequences of their joint probability, because if I sum a probability mass function over all possibilities, I get 1. Of course, if I restrict this sum to the typical sequences, which is a subset, well, I get something less or equal than 1. But now I have a uniform lower bound on these probabilities given by the asymptotic equipartition property. So I just replace these probabilities with the uniform lower bound 2 to the minus n times entropy plus delta epsilon, right? And so since now if I do this replacement, these terms are all equal, here I just have the number of terms in this sum, which is the cardinality of the typical set, times this 2 to the minus n h x plus delta, okay? And then what I have to do is simply multiply here and get an upper bound, because now I have the cardinality of the set is less than the inverse of this, which is exactly this upper bound, okay? For the lower bound, I have to use the fact that because of the law of large numbers, this probability, the probability that a random sequence is typical, goes to 1. Because a probability a random sequence is typical means the probability that the empirical frequency, the empirical frequencies of for all letters converge to the true probabilities, and we know that this goes to 1. So basically that's the same statement, simply written in a different way. The probability that a random IID sequence is typical goes to 1 when n goes to infinity. Which means that for every epsilon, what is this? For every epsilon greater than 0, there exists some n epsilon such that for every n greater than n epsilon, the following is true. If we have something that a probability that goes to 0, it means that for sufficiently large n, so for an n sufficiently large, this probability will be greater or equal than 1 minus epsilon. Because if this goes to 1, it means that at some point, for sufficiently large n, the value of this probability will be sufficiently close to 1. Okay? So that's just a definition of limit. And now we can simply write this probability explicitly. What is the probability that a random sequence belongs to a set? Well, that is simply the sum over all possible sequences over the set or of the corresponding probabilities. And the probability of an event is always the sum over all elements forming that event. The event is the set, is of the corresponding probabilities of all the elements. Here the elements are sequences. So this is greater or equal than 1 minus epsilon, but now I have a uniform upper bound to these probabilities by using the asymptotic equipartition property in the other way. So we have a uniform upper bound. Before we had a uniform lower bound. So now we can write these as cardinality of the set times this uniform upper bound, which is 2 to the minus n h x minus delta, and this is greater or equal than 1 minus epsilon, and then I simply multiply this here and I get my lower bound. And this holds for sufficiently large n. While the upper bound always holds, this is always true for every epsilon greater than 0 and n. You know, there may be in some cases, you take epsilon too small or n too small, the typical set may be empty, and so its cardinality is 0, but 0 is less than this exponential, so this is always true. But in this case here, this is true for sufficiently large n, okay? Good, so this proves this cardinality bounds on the typical set. And at this point, we can basically give the following graphical interpretation. We have the set of all possible sequences over a certain alphabet. So this is the set x to the n of cardinality of x to the n. And then it turns out that some of these sequences have the property of being typical, so with empirical frequency close to the true probability. So this is in general is a subset, and this subset is exponentially smaller because the size of the set is in the exponent 2 to the n times the entropy. Now, if you remember, these can also be written as 2 to the n times log base 2 of the cardinality of the set, and we know that in general the entropy is always less or equal than log of the cardinality of the alphabet. So in other words, the exponent here is smaller than the exponent here, which means that this typical set is exponentially smaller than the set of all possible sequences. In addition, the probability mass, we see that it distributes quite uniformly here, in the sense that for any point, any specific typical sequence, its probability is 2 to the n to the minus n times the entropy, right? But now if I sum over all the typical sequences, I have roughly 2 to the n entropy sequences. Each one of them has probability 2 to the minus n times the entropy. I find 1, okay? Well, this is not exact because we have these epsilons and deltas to take into account, but this means that this set concentrates almost all the probability mass for large n, which means that sequences that are not typical, overall, not just individually, overall, if you sum over all the non-typical sequences, you find a very, very small probability, much smaller, in fact, a vanishing, exponentially vanishing probability, which means that for very large n, the event that a non-typical sequence occurs is an extremely rare event. And in fact, its probability goes to 0 exponentially fast with n. Okay? I hope that this is clear. This is really essential to understand the sort of very special behavior of long random sequences. So if I want to extract a qualitative thing to remember here, of course you also need to know the quantitative things and the formulas, but the qualitative concept here is that despite a single random variable has, of course, a random behavior, is like a random number generator. You cannot really predict very surely what this number with this random variable will be. right? Because it's a random event. Say you have a, I don't know, a binary random variable that generates 0 and 1 with probability 0.3 and 0.7, okay, you know that a priori, well, we expect to see with higher probability a 1 than a 0, but if I don't tell you anything and then you flip this bias coin, well, you still see some zeros, some ones, and every time is you can't really predict. But if I consider a very long sequence of these randomly generated numbers, well, it turns out that when n goes large, these sequences have a much more deterministic behavior. Almost surely you see a typical sequence. And a typical sequence is a sequence with the empirical frequencies of zeros and ones very close to what the distribution, the probability mass function of the random variable tells you. So we expect, if I generate a million of random zeros and ones with that distribution, I will expect to see 30% of zeros and 70% of ones with some small fluctuations. Okay? So we conclude here, and the rest will be in the second part.